Hello, I'm Huub Toussaint, and I like to talk about the biomechanics of drag and front crawl swimming with special reference to wave drag. And now you may wonder, wave drag? What is that? Well, let's first look at drag acting on a swimmer. And here you see some swimmers swim. And what is immediately obvious is that if we swim on the surface, we create waves. But there is also pressure drag and friction. So total drag of a swimmer has three components: swimming at the surface, friction, pressure drag, and wave drag. And if you look at this left video, you can see that some wave making resistance may be very considerable. So it is maybe very interesting to look at these different components and raise the question how large wave drag will be at maximal speed. Now let's dive a little bit deeper into the forces involved in swimming. And what you see here in this slide is a free body diagram of a swimmer in which the various forces acting on this swimmer are drawn. In the vertical plane, you see buoyancy and weight. And let's assume these cancel each other nicely out. And in the horizontal plane, you see the swimmer is generating propulsion to overcome drag. And of course, if you were swimming at constant speed, the average propulsion will equal the average drag force, although they're in opposite direction. And now the question is, how large is this drag? And therefore, how large is this propulsion? Is there a way to measure it? And let's go into measuring of drag while swimming. And in the next slide, you can see how we made a contraption to do that. And it's called the MAD, the MAD system. It's of course a reference to the crazy professor who invented it, but it's also standing for measuring active drag, so the drag while actively swimming. And what you see in this left video is a swimmer swimming along push-off pads, and the system is instrumented such that it can measure these push-off forces. And on the right part of the slide, you see an exploded diagram of the system. You see a swimmer swimming along the, you see a picture of a swimmer pushing off from a pad, and you see a top view of the mat system in a 25-meter pool, and you see below that the forces recorded while swimming along these 16 pads. What you also can see in this force recording is two vertical lines, dotted lines, which indicate the start of the push-off on the second pad and the start of the push-off on the last pad. And since the distance between the second pad and the last pad is 18.9 meters, and you know the time, you can also calculate the average velocity the swimmer uses to travel that distance. So what we can do then is measure the average force for that velocity given the recordings that we have made. So in this way, and by repeating this procedure for the swimmer at different speeds, we can determine the relationship between the velocity and the drag required to swim at each velocity. So this is the way we measure the active drag. This is, of course, the total drag, including friction, pressure drag, and wave drag. And let's now move on a little bit to wave drag. And to do that, I like to make a small adventure into ship building and see how ships create waves and how that affects their total drag. So we're now going to look at the ship. And what you see here is a ship traveling to the right with a specific velocity at the surface. And now, why is a ship creating waves? Well, if you look at this red line, you see that there are different pressure points. There's a pressure point at the bow, and there is a pressure point at the stern. These are both positive pressure points, and there are two negative pressure points at the shoulder and the quarter. And these all generate waves. So you have the bow wave, the shoulder wave, the quarter wave, and the stern wave. And these are summed, and these form the total wave system that's traveling with the ship and creating the drag of the ship. And in addition to that is, of course, also the friction and the pressure drag. Now it's interesting to look at what happens if the ship increases its speed, because there will be an effect of speed on wavelength. Here you see the speed traveling at speed v, and you see that there is a bow wave traveling along the length of the ship. And what happens now if we have the ship speeding up? So if the ship is traveling at a larger velocity, then ultimately the length of the wave is equal to the length of the ship. And the ship is more or less trapped between the bow wave and the stern wave. And if that happens, then it's very difficult for the ship to travel any faster, because it then has to climb over the bow wave. And so when a ship is traveling at the hull speed, the speed at which it's trapped, then 70% of total drag will be wave drag. So that's very considerable. And there's only one solution for a ship to do that, and that's go over the bow wave, and that's what speedboats do. But normal ships, they evade more or less traveling at hull speed because it's very costly energy-wise. Now there are some basic principles that you can apply, because the length of a surface wave will equal lambda, and that's equal to 2 pi times the velocity squared over over g, and g stands for the gravitational acceleration. So you can recast this formula, and then the hull speed for a given length L of a ship will be Vh is equal to g, the length of the ship, divided by 2 pi, and there the root of it. And now it's interesting that what applies to ships should also apply to swimmers. So you can calculate the hull speed for a swimmer. Now let's do that. And let's assume we have a very tall swimmer, a swimmer of 2 meters. And then we can do the equation, and we can calculate that the hull speed of a swimmer with a height of 2 meters is 1.77 meters per second. Now you will soon realize that if the world record on 100-meter freestyle swimming is below 50 seconds, that approximately a speed of 2 meters per second is attained swimming. You have to, of course, discount a little bit for turns and the push-off and the dive, etc. But you can immediately see that good swimmers, like for example our Dutch swimmer Pieter van der Hogenband, swims at speeds in excess of 2 meters per second. So this is rather strange, because ships or boats have difficulty swimming or going faster than their hull wave, and swimmers more or less go faster than hull speed. How can it be? Well, let's look a little bit at a very good swimmer. And here in Holland, we have, of course, Pieter van den Hogeboom, and he was so kind to illustrate swimming at different speeds to see what's going on if you look at the wave formation. So you see here waves formed at his head and also at his buttocks and maybe a little bit at his feet. So you see a very nice formation of different waves. And now we ask Peter to swim a little bit faster and see how his wave formation changes. Because now he's swimming about 13.5 seconds on 25 meter. And now he's going to swim much faster, and you see a very big difference in how the waves are formed. The midship wave is gone, and actually there are now two waves formed, one at the head, so one at the bow, and one at the stern, one at the feet. So this is a very nice illustration how speed, swimming speed of a swimmer changes the wave formation at the surface. Now let's summarize a little bit and then dive a little bit deeper in what's happening. So, what's the summary? Humans can swim faster than hull speed. And the next question, of course, is okay, so what? How important is wave drag? So, is it a big thing? And if so, is there a way to decrease the wave drag? So, can technique influence wave drag? Now, the last question has been examined a little bit in Japan. And how did they do that? They made a small buoy and they measured just the acceleration of the buoy while swimmers were swimming in the lane alongside. So they calculated an average of the wave power, so to speak, and they did that for different swimmers. So here's the graph showing a little bit the amount of wave formation by recreational swimmers at different speeds. So you get a blob of different dots, which are representative for recreational swimmers. But they had also middle class swimmers, and you see that the blob is going a little bit to the right, but also a little bit going down. And then there was, of course, elite swimmers who can swim much faster, and then there's much more wave formation at the high end of the speed, but also at the lower speeds, you see that the blue dots are very much lower than the orange dots of the recreational swimmers. So Takamoto, Omichi, and Miyashita, my Japanese colleagues, did a very interesting study which suggests that if you are more able to swim, so if you have a better technique, you're also able to swim at higher speeds. But if you swim at comparatively similar speeds, then the wave production is lower for elite swimmers in relation to recreational swimmers. So that was very interesting, and therefore we tried to measure wave formation by swimmers by looking at the height of the waves produced by swimmers using a video setup that's depicted here in a pool in Amsterdam. But that was rather, let's say, difficult. It was a difficult setup. We didn't get very accurate measurements, and it was very cumbersome. As you will realize, that video analysis is most of the time very difficult and consumes a lot of time. So we abandoned this project. And we were looking for a new way to measure wave drag as part of total drag. And we got help from our friends from the Technical University in Delft, also in the Netherlands, who came up with the so-called longitudinal wavecut method. And this is an experimental method based on the potential theory, and the theory is detailed in a paper published by Mr. Eggers in 1967. And in Delft, they do a lot of shipbuilding research, and they develop this method to determine how much wave drag is part of total drag for ships. And let me try to explain a little bit what the idea is behind this longitudinal wavecut method. Well, what they say is we have a control volume, and in this control volume, energy is produced in the forms of waves. And if we do the analysis such that the waves only are leaving the control volume to the sides, we may have a way to measure the total wave drag. So step one is that we assume a point where waves are made at a zero velocity. But then we start to move, so there is a velocity. And what you see is that if this control volume is stretched, so to speak, there will never be energy leaving on the top and also never on the bottom part of the control volume. So energy is only leaving at the sides. And so there is no energy at the bottom, at the top, and no at the bottom. And if we assume that the waves are symmetrically formed in the center of the control volume, then we only have to measure on one side and double that value to get the total wave drag. So the basic idea is to place on the side of a swimmer swimming along a track devices to capture the wave height. And here you see the rig incorporating 3 snares that measure wave height. And here you see other pictures giving an impression of how we set it up in the pool. And here is an exploded diagram. So what you see here is we had the magnet system installed in a 25-meter pool. And on the right of that, you see that there are wave height meters, 4, which were positioned as a specific distance from the track of the swimmer. And we had 2 conditions: swimming on the mat system at a distance of 2.19 meters, and we had the swimmer swim free at a distance of 3.25 meters. Okay, so this was how we were going to measure total drag using the mat system and estimating the wave drag produced while the swimmer was swimming on the mat system. So we could then have the total value and the wave drag value. And in the next slide, you have a visual impression of how we were doing that. So these are the snares measuring wave height, and then a swimmer swimming on the mat system at very high speeds, above world record speed, because it can push up from fixed points, and you can see these waves formed. And here you see that we measured wave height while they were swimming. So maybe again the impression of what's going on. Very fast swimming, enormous waves produced. We measured at the same time total drag using the mat system and measuring separately the wave drag. So that was the longitudinal wavecut method in action together with the mat system. And results are also depicted in one drawing. To the right, you see that the time or the number of samples is on the horizontal axis, and there is a voltage signal on the vertical. And what you see is that we measured push-off forces with the blue line on the right part of the diagram. So starting about, let's say, 150 samples and ending about 1100 samples. So that part is the recording of the drag on the mat system. And the waves are formed and they have some time necessary to travel to the capture point. And you see that there is still water where there are no waves reaching the capture point. And then there is a signal that we are used. And then there's also part of the signal that's a reflection of waves coming back from the side of the pools. So there is a still water, and then there is no waves analyzed, and there is a use signal for the wave drag, and then the reflection is ignored. Well, one way or another, we use the signal to make an estimate of how much wave drag was formed by the swimmer, and we plotted that together with the measured total drag of this swimmer. And that's given here in this diagram. And what you see here in black with the black dots is the drag measures when we were using the arms only. And normally we don't allow the swimmer to use the legs because that would add a force that we cannot measure. So drag measurements are done swimming arms only, and the small buoy is keeping the body aligned. But in this condition, we were also studying the effect of the kick. So we were swimming on the mat system with arms and legs. We were swimming freestyle arms, and we were swimming freestyle arms, legs. And so what we were going to analyze is what the total drag was and what the wave drag was. Now the total drag is given in this red line, and maybe I was not clear. The lower lines with the black dots are the estimated wave drag as part of the red line. The red line is the total drag of this swimmer. Sorry about that. The blue is the drag when the swimmer is not swimming on the mat system. So what you see is that the free arms blue dots are the wave formation created when not swimming on the mat system. So you see at comparable speeds, the wave drag is almost equal to that of the wave drag swimming on the mat system. Now we also can see what happens when we swim free arms and legs. And of course you're going to swim a little bit faster, and what you see is that the wave formation is also larger than when swimming arms only. Now look at what happens when you swim on the mat system, arms and legs. And again, we're swimming much faster and maybe even above world record speeds for these swimmers. And what you see is that there is considerable wave formation. But it seems maybe not as much as what's normally expected. So we have here a comparison of wave drag for different swimming modes. Swimming mat system on the mat system with arms, swimming on the mat system arms and legs, swimming free arms and swimming free arms and legs. And now what's interesting is that when you swim on the mat system, wave formation jumps up when you swim arms and legs. So these blue squares are going up tremendously. So in summary, humans swim faster than hull speed. Wave drag matters at competitive swimming speeds, but seems less than 70% of total drags observed in ships. And so it's maybe not as important as, and so maybe not as bad as we feared it would be, but still it is a considerable part of total drag while swimming. So wave drag, especially at the higher speeds, is really mattering, and if we could reduce that, then maybe we could swim even faster. So the next question is, do we have now cues? Do we have cues that technique could have an effect on wave drag? Or in other words, could non-stationary effects related to technique reduce wave drag? Now in shipbuilding design, there is a technique to reduce the bow wave formation. And maybe a similar principle is operative in swimming. In shipbuilding, you have a bulbous bow, and I'll show you the bulbous bow. What's the principle of the bulbous bow? It's a protrusion below the waterline, and what's happening is that water is accelerated. You see small arrows at the right, which grow when they pass along the top of the bulb. And so what happens is that water speed is accelerated, is increasing, and you may remember the law of Bernoulli, that pressure and speed are related. Low speed, higher pressure; larger speed, lower pressure. So what you see is that this bulbous bow has the effect of increasing speed of water and thereby reducing the pressure point that sets up the waves at the bow. So in shipbuilding design, there is a principle of a bulbous bow, which reduces bow wave formation. Could it be that the arms, the gliding arms, function as a bulbous bow, reducing the height of the bow wave? Well, it could be. But it may be interesting to look a little bit more at non-stationarity of rostral pressure point, and that it's non-stationary in the sense that in ships the ship hull is always the same, has the same form, is always in the same position, and in the swimmer it's moving about. And so therefore the pressure point is also moving about, and therefore it inhibits build-up like it would build up in a stationary situation of a ship. So the non-stationarity of the rostral, so the forward pressure point, prohibits full build-up of the bow wave, probably. But could a similar principle be operative at the rear of the swimmer? So what is the effect of the kick? What is the effect of the leg action? And this is interesting because we did the comparison of total drag. We looked at the wave drag in red, and there we also looked at the effect of the leg action for some swimmers. So for some swimmers, you could see that if they were not using the kick, they were swimming at considerable speeds, but you see that the round green dots at the right are close to the red line. But as soon as the kick is involved in swimming, the swimmer is able to swim much faster, even at speeds in excess of 2 meters per second. But what you see is that the increase in speed is not going together with a large increase in wave drag, at least for the square green filled squares. So it may be that one way or another, some swimmers have the skill of using the kick, maybe not even so to add to propulsion, but rather to reduce wave drag formation at the rear of the swimmer. And that could be very helpful to swim even faster. To illustrate this point, I have here two pictures. And this is a picture of a swimmer rather fast, but without using the kick. And what you see here is that when the swimmer is using a whole stroke on the right, the swimmer is going faster, but without a concomitant increase in stern wave height, suggesting that one way or another, the kick is helpful in reducing wave drag formation. So, the leg action might disrupt the pressure pattern at the stern, prohibiting a full buildup of the stern wave. Now, there is another very interesting and curious aspect of wave drag, and that's related to why we use the so-called MAD system to measure drag, because a lot of engineers will immediately ask the question, why do you do it so difficult? Why not tau a swimmer and determine drag by just towing the swimmer? That could be easy. That's much easier than having the swimmer swim with all these pads and difficulties, and a towing rope is much easier, and you can much more easily determine the drag of the swimmer in a passive fashion. Now let's revisit it. Let's revisit our ship and look at this question a little bit, because there is something interesting going on. Because if the ship is sailing or going at the water surface with a specific speed, you can imagine that for different velocities, different wavelengths are set up along the length of the hull. And so here is a length of ship L with wavelength lambda. And you see that the bow wave traveling along the length of the ship eventually reaches the stern wave, and there the stern wave and the bow wave have the same movement. In contrast, you can imagine that if you go a little bit slower in this case, the bow wave is a little bit shorter, and where in the first instance there was reinforcement, the stern wave is now cancelled by the bow wave. So what you see is that at different speeds, the ship will exhibit different forces due to reinforcement of cancellation of the bow wave with the stern wave. So here you see it in the diagram. So there's first reinforcement with K is 1, and then K is 2, there is cancellation, and K is 3, again reinforcement. And K is 1 is of course the whole speed. And then you have reinforcement, so a lot of wave drag formation, cancellation, reinforcement. And this gives the characteristic passive drag measurements of a ship, where you see that the wave-making resistance of a ship when towed is generating humps and hollows along the drag curve, where you see K is 5, K is 4, so different humps and hollows that are created by the cancellation and reinforcement of the bow wave and the stern wave. And K is 1 is again the whole speed. And now let's look at passive measurements that I did in Colorado Springs in 1988, a long time ago. And we measured passive drag, and we did that for a subject with his head low and his head high. And what you see here is, again, humps and hollows, depending on the velocity of the water, because this was in a swimming flume, so there was no towing in the sense of dragging the swimmer along the water, but the water speed was increased and the drag was measured by a force transducer. So this is when the head was low, and if you just tilt the head just a little bit, it's only maybe a couple of degrees, you see this kind of recording. Again, you see very clear humps and hollows, probably due to reinforcement and cancellation. And I don't know what happens on the right side of, maybe it is cancellation and reinforcement all the way there. I don't know. But just for reference, for the same swimmer, we also determined on the same day the active drag using the MAT system, and these were the results swimming on the MAT system. So there may be a big difference between active drag and passive drag, and because if you measure in a passive way the drag, you have problems with both a good alignment of the head, which may have a huge effect on total drag formation, and the other aspect is that you have cancellation or reinforcement of the bow wave with the stern wave, creating also all kinds of disturbances on how you have your drag values measured. Well, these are some aspects of wave drag. I hope it proves interesting. Please read the accompanying text, and if you have any questions, I'm happy to serve them. And thank you for your attention.